Alright guys, so now we're going to hit the beginning of oceanography. So we're going to look at that fact that oceanography is the scientific study of the Earth's oceans, and we explore it in a variety of ways. We use sonar, we use satellites, and we use something called submersibles. So sonar is something called sound navigation and ranging. It's based on the echo ranging of bats. The idea is you send out a pulse from the ship into the ocean. The sound moves through the water. It bounces off the ocean floor, and then you time it to see how fast it's going to take for that bounce to go from the bottom where it hits back up to the ship. The deeper the water is, the longer it's going to take. And we know how fast that sound moves through water, so it's actually a really basic mathematical calculation, and you can actually get depth from that. We also use satellites that orbit the Earth. One satellite is called CSAT, was launched in '78, and allows scientists to measure the direction and speed of ocean currents. And another one called GeoSat, it was once a top secret military satellite, and allows scientists to look at slight changes in the ocean surface. And the idea is that if you have something like a trench, which is a deep pit in the ocean floor, the height above that is going to dip down just a little bit. Nothing that you could tell like from the surface. But if you have a satellite, and the detail you can get from satellite, especially a former top secret military satellite, you can have an idea. And it's a way to actually map the ocean floor that's probably a lot faster than using sonar. We also use some underwater vessels. They're small, called Alvin, Deep Flight, Jason II, and the Medea. And Alvin is around 7 meters long and has been used to look for sunken ships, recovery of a lost hydrogen bomb. How we lost that hydrogen bomb, I don't know. And looking at the ocean floor in general. Deep Flight looks like a mini airplane, underwater airplane, and can go down about 11,000 meters. And the Jason II and the Medea are actually robotic. So you have someone on the ship who has like joysticks, and it's like a video game for them, and they're piloting the Jason II using that, and the Medea actually kind of hangs out on top of the Jason II and is attached to it with a tether, and then you can actually have it go off and do its own thing. And Jason, it's doing its own thing. A lot of times you use the Jason II and the Medea when it's too dangerous for a human to go down. I mean, it's dangerous, period, but there are certain times and areas which is way too dangerous for us to go down, or too expensive even. So you see a picture of the Deep Flight on the top left, and there is Alvin on the bottom right. I have people next to him because I wanted you to get the idea of size, and I could not do either of these. I am too claustrophobic, and the idea of being trapped in one of these in a situation where you can't get out I would not be well for it. And here I also want you to take a look at this. You can see it moving in the water. This is the Jason here, and the robotic ones. So why do we care about the ocean? Lots of reasons. One of the PowerPoints you're going to be going through talks a little bit about why you would care. I mean, resources and major amounts of resources for us. Even if you don't really want to deal about the environmental effects, think about what we're getting from the ocean. So if we screw it up, we're screwing that up too. It covers 71% of the Earth. That's huge. You got a list there of your major oceans. Your Pacific is the largest. Seawater is around 96.5% water and about 3.5% salt. Surface temperatures range depending on where you are in the ocean and what depth you are in the ocean. And the density of the seawater also changes depending on temperature and what's in the water itself. The colder the water is, remember, anytime you have anything that's cold, the atoms draw in closer together. So you have denser air, you have denser water, and then you add salt to it, it even makes it more dense. Temperatures obviously get colder as you go down. If any of you guys have been swimming in a pool in the beginning of the pool season, you probably dipped your foot into the water thinking, oh, it's not so bad. It's actually kind of comfortable until you take that dive in. And when you dive in, you discover that first foot or so isn't so bad. But as you go deeper into the water, it is freakishly cold because it hasn't had time to warm up yet. We divide the layers of the ocean according to obviously depth, but also temperature. And your top layer is your epilimium. Oh my goodness. It's your surface layer, your warmest layer, where you find a lot of life in the ocean. Then you have your thermocline. That's a transitional layer where you kind of go in between the warmer top layer to the really freakishly cold bottom layer. And that's your hypolimnium. In the ocean, you have currents, which are streams of movements of water that occur near the surface. These guys, the surface currents, are controlled by these huge winds called global winds, the movement of the Earth, and the Coriolis effect. And when these waters actually, as they're moving, run into islands or run into continents and are deflected, kind of like in a pinball game when the little ball hits a bumper and it gets deflected. The water, as it moves, as it's hitting a continent or large landmass, it gets deflected. You also have currents that are really deep. They're towards the bottom of the ocean, and they are dealing with temperatures. So what you have going on is you have at the poles, you have very, very cold water, and that very, very cold water actually starts to move along the bottom of the ocean towards a warm area, like the equator. And as it reaches towards the equator, it starts to warm up. And when it warms up, those atoms move apart. It starts to become less dense, and it rises up. As it rises up, it starts to move back towards the poles, the cold area. And as it gets towards the cold area, those atoms then start to move closer together, become more dense, and then sink down. All right, those wind-driven surface currents affect the first few hundred meters of the ocean. You can have something called an upwelling, and that occurs when winds push surface water aside and the surface water is replaced by really cold, deep water. This happens with El Nino, or I should say, the lack of this fails to happen with El Nino. You don't get the upwelling occur in the Pacific Ocean off the coast of South America. And when you do this, you have all sorts of fun and exciting issues. It alters weather patterns around the world, so you have areas that are normally very warm and wet, and they now become dry. And you have areas that are dry get tons of rain. And you think, well, at least the areas that are getting tons of rain, that's good for them. Not really, because the land can't soak up all that rain, and you end up having flooding and all sorts of problems with that right there. And you're also having lots of issues with the crops in the areas that are dry and crops for the areas that are flooding, and it's economically a huge problem for the people living in those areas. So gyres. I mentioned this in another of these PowerPoints, and these are basically closed circular currents. And basically you end up, you'll have a current move in this area, and literally the water kind of gets trapped in this circular, almost like conveyor belt type of path. And this is an issue when you're dealing with trash, because there's an area called the Great Pacific Garbage Patch, and it's due to the gyre you see right off the west coast right there of our country. And this nice movement of water grabs that trash and ends up kind of dumping it all in this one area, and it's crazy pollution. All right, ocean waves. Ocean waves are caused by the wind. The water in a wave moves in a circular motion. It doesn't necessarily move forward. The energy is moving forward. There are parts of the wave there you see on the left-hand side. You have the trough, which is the bottom of between two waves. The top of the wave is called crest, and the length between the two waves is called your wavelength. The distance from the trough to the crest is your wave height. And last but not least, we're going to talk a little bit about ocean tides. They're caused by the gravitational attraction among the Earth, Moon, and Sun. And depending on the line up of the Earth, Sun, and Moon, you're going to have worse tides or greater tides than other times. Lunar tides are twice as high as solar tides. So if you see here in the top picture, the sun and the moon aren't lined up. They're kind of perpendicular for each other, so you don't quite have the strength of pull of the gravitational forces of both the sun and the earth. But if you look on the middle one, you got them lined up right there, and that's your spring tide. And you end up having high tides that are higher than normal, lower tides that are lower than normal. And then another way to have a spring tide is when you have, they're still lined up, but kind of on opposing sides in the same sort of thing. The lineup of the gravitational forces that cause a higher tide than normal. Alrighty. There is your PowerPoint.